So the first thing I kind of want to get to today is I want to talk a little bit about some project stuff. Um, I should hopefully have everybody's survey results uh, today. And the next thing that we need to do is the linear regression. So um, basically, if you guys remember earlier in the semester, we did a worksheet on linear regression. It had to do with selling, I think, roses, right? And you surveyed people and got their how much they would pay for their product, right? So essentially, what I want you to do is I want you to follow basically the exact same steps from that activity with your project data, all right? Um, so the sort of details are in the linear regression task in the handout I gave you guys. Essentially, you're going to accumulate all that data. You're going to put it all together, and then you are going to get a demand function that you can sort of use to figure out what prices you should be setting things at. Okay. Um, so essentially you should be following the blueprint that we did on that class a while back. I will post that. I can post that handout again into Discord so you guys can take a look at it if you're stuck on anything. Um, and then if you guys have any questions on how to do that, you can definitely chat with me, and I'm happy to help you out with your data and stuff. So. Um, I don't think I'm going to move the due date on this. This task is actually not that difficult. There's not that much to it. Um, Once you have your data in hand, it's just a matter of actually accumulating those data, right? So I think I'm still going to have it due next Wednesday. So that'll be due on the 22nd of April. And I'll throw up a Dropbox for that. Um, does anybody have any questions about how what we're doing so far with the project or anything along those lines? Okay, so today I wanted to cover an I wanted to cover one possible application of integration. And I'm going to give you guys, instead of a big pile of homework problems to do or practice problems to do today, I'm actually just going to give you guys a quiz sort of thing. It's not really a quiz in that, like, it's not going to take 15 minutes and you're not just going to be sitting there doing it while I watch you, but it will be a quiz grade. It's sort of like a mini project thing. And on that, you can either work in your project groups, you can work independently, you're allowed to consult outside sources. Basically, I just want you guys to work through it, make sure you can get it. And the topic I want to discuss for this application of integration is called the Gini Index. The Gini Index is named after a statistician. His name is, I believe, Lorenzo Gini, Italian guy. And what it basically is it measures wealth inequality. So it's a number between, so it's a number between 0 and 1. And the bigger it is, the less wealth, the less equity there is, or equality there is. And basically, the way the Gini index is calculated is you take the straight line y equals x, that passes through the points 0, 0, and 1, 1. And then you're going to, basically what you do is you build something called a Pareto curve. It's a logarithmic curve, or a logarithmically calculated curve anyways, that passes through the points 0, 0, and 1, 1. And the Gini index is, you take the area between the two curves and then you multiply that by 2. The only reason you multiply the area by 2 is because you want it to be a scale between 0 and 1 rather than a scale between 0 and 0.5. And basically the idea behind this Pareto curve is that if every single person has the exact same amount of income, then the curve that you end up with ends up being that straight line, this line of total equality. But if you had some society where, say, 99 people had no money at all and one person had all of the money, then your curve would look like this. There would be no area underneath that curve. It would be flat horizontal and then flat vertical at the very end. And the area here would be 1/2 of the base times the height. It's just a triangle, right? So that's 1/2 of 1 times 1, which is 1/2. So if one person has 100% of the wealth, the Gini index is 1. If everybody has an equal share of the wealth, the Gini index is 0. So in general, the Gini index will be somewhere between 1 and 0. It will basically never be either 1 nor 0. Usually tends to be somewhere in between that. Okay. So for example, suppose there is an island society where wealth is measured in seashells. And 5 people live on the island. We're using 5 people on the island and this weird seashell thing just to sort of simplify the model a little bit and make it a little bit easier to follow. What we're actually going to do when we actually measure the Gini index for a society is we're going to take wealth quartiles or quintiles, and then we're going to sort of fit this to the same model. Okay. But here we have our island society where wealth is measured in seashells. There's 5 people on the island. Of those 5, we have 5 people. A, B, C, D, and E. And person number A, or person A has 5 seashells. Person B has 10 seashells. Person C has 15 seashells. Person D has 30 seashells. And person E has 50 seashells. Okay, so there's some wealth inequality here. Everybody doesn't have the same amount of seashells. Person E has half of the seashells, and everybody else is sort of distributed between each other. Some people have a little less, some people have a little more. Okay. In order to compute our curve, we want to basically accumulate this data. So step one, we want to accumulate this data. So essentially what I want to do for A, B, C, D, and E, I want the number underneath them to represent the amount of money they have plus the amount of money held by everybody beneath them. In other words, I want to know how much wealth is controlled by the bottom 20%, the bottom 40%, the bottom 60%, the bottom 80%, and the entire population. Okay. So the bottom 20% is just person number A, and they control 5 seashells, right? The bottom 40% is person A and person B, and together they control 15 seashells. Person B controls 10, and person A controls 5. The bottom 60% is A, B, and C, so that's 30 seashells in total. The bottom 80% is A, B, C, and D, and they control a total of 60 seashells. And then the entirety of the wealth is 110 seashells. And then second, we're going to write the data. So write the accumulated data as a proportion. I'm not interested in the total amount of wealth. Like I want my curve for my Gini index. I want it to go through this point 1, 1, and this is going to represent the point which is 100% of the population and 100% of the wealth. Okay, so basically for each of these numbers, 5, 15, 30, 60, 110, we're going to divide them by the total, right? So 5 over 110 is, so we have 0.2 and 0.45 repeating. For 0.4, we're going to have 15 divided by 110, which is 0.136 repeating. For 0.6, we'll have 30% of the wealth, which is 0.27 repeating. For 0.8, we'll have 60 out of 110 for the wealth, which is 0.54 repeating. Sorry, this was not 0.45, this was 0.045. And then finally, for 100% of the wealth, we'll have 1, right? So we'll have the 0.11. And what we could potentially do with this data is we could plot it. So here we have 4, 5, 4. Here we have 1363 or 1364. Here we have 0.2727. Here we have 0.5454. Here we have 1. Let's make that bigger. And you can see our data plotted here, right? So if we want to draw that graph, let's say down here, 2, 6, 7, 8, 10. So that'll be at 1. So our top point will be up there at 1. So we have 0.2, 0.4, 0.6, 0.8. At 0.2, we had 0.045% of the wealth. So that's going to be like right about maybe here, a tiny little bit less than half. At 0.4, we had 0.136. So that's about a third of the way up above 1. Here we had 0.27. So that'll be right around here, about 2/3 of the way between 2 and 3. For this guy at 0.8, we had 0.54, so that'll be 3, 4, 5. That'll be right around here, maybe just a little bit less than halfway between 5 and 6. And then our last point will be at 1, 1. So something we could do here is, instead of actually generating, so we could draw the line of total equality, right? Which is, whoops, did I do something wrong here? Yeah, I did. Okay. Sorry, I went one step too far. So there's our line of total inequality, and we can sort of estimate what the curve should look like by drawing line segments between each of these. So we kind of get those trapezoids that we saw last class when we were talking about finding area beneath the curve, right? And to estimate the area that we need for the Gini index, what we can do is we can sort of split this up into triangles and rectangles. And use some geometry to estimate the curve. So we can split into geometric shapes. Then estimate area. So one thing is certainly true. In order to estimate the area in the middle here, we're going to have to take the area of the triangle, which is the area under the line of total inequality, and then subtract the area underneath our Gini, our curve here. Okay. And the area underneath this curve is what we're estimating using these geometric shapes. So I'm not going to do all of that work right now because it would take a while to sort of split them up into all the little triangles and stuff. However, it's something that is definitely very doable. But there is a slightly better way of doing this. Instead of using exactly those points and just making those harsh lines between them, we can generate a Lorenz curve. This is a type of curve that passes through 0, 0, and 1, 1. And it's something that we can use like a calculator to sort of find it's like a curve of best fit, basically. So we can take the data points that I plugged into um, Desmos here, and I've set it up so that it spits out the formula of the Lorenz curve here. A Lorenz curve is y equals 1 minus x to the power of a, where basically a is going to be computed based on what your data is. So for this curve here, when we try to fit it to that curve, we end up with y equals 1 minus x to the power of 0.407. So essentially, we're using this curve here, this black curve, to approximate our population. And then finding the area beneath that curve. So we can find the area beneath this curve by using integration. In other words, our picture here, we have our Lorenz curve and we have our line of total inequality, or line of total equality. If we call this area A, this is 1/2 minus A. And A is equal to the integral from 0 to 1 of 1 minus x to the power of 0.407 dx.
Where did the 0.407 number come from?
So that 0.407 came out of our calculator here. Do you see where parameters here it says A?
Yeah.
Okay. So that's the output from the curve fitting tool we used. That's what told us it should be 0.407. That will vary depending on what your actual data set is. For this Seashell Island villager thing, it is 0.407. Now, to actually compute this integral, that's a little bit tricky. We are going to talk a little bit about substitution in the coming weeks, which is really the technique that you need to use to do this. But right now, and this is in the quiz I'm handing out, the integral of 1 minus x to the power of a is equal to negative 1 minus x to the power of a minus 1 divided by a minus 1 plus a constant. Sorry, that's a plus 1 over a plus 1. You're applying the power rule, but because the x is negative inside of this, you actually have to add, or you have to pull out the negative sign, essentially. It's kind of like the chain rule. We'll talk more about this later on, but right now we're just going to take this as a fact. Like, this is an integration formula that we know to be true. So now we can do our integral. That means that, so the integral of 1 minus x to the power of 0.407 dx from 0 to 1, we can split this up into two separate integrals. We have the integral of 1 minus the integral of this thing. So that's the integral from 0 to 1 of 1 dx minus the integral from 0 to 1 of 1 minus x to the 0.407 dx. Just like we can split derivatives across sums and differences, we can also split integrals across sums and differences. The integral of 1 from 0 to 1 is just going to be x evaluated between 0 and 1 minus this integral here. We can use the formula above, right? So this will be negative 1 minus x to the power of 1.407 divided by 1.407. And again, this is evaluated between 0 and 1. Okay. So one quick thing we can do to simplify stuff up a little bit. The minus and the minus here are going to cancel. So we really have just x evaluated from 0 to 1 plus 1 minus x to the 1.407 divided by 1.407 evaluated between 0 and 1. The first part here is pretty easy to check. X evaluated between 0 and 1. When we have this bar, remember that means that we're just plugging in 1 minus 0, right? So we're plugging in 1 and evaluating, and then we're plugging in 0 and evaluating, right? So that part is just 1. So this is 1 plus something. And then our other part here, this is 1 minus x to the power of, let's draw an arrow there. It's actually there. 1 minus x to the 1.407 over 1.407 evaluated between 0 and 1. That's going to be 1 minus 1 to the power of 1.407 divided by 1.407 minus 1 minus 0 to the power of 1.407 divided by 1.407. This part here, 1 minus 1 is 0, so this part's just going to disappear. This part here, 1 minus 0 is 1. 1 to the power of anything is just 1, so this is 1 over 1.407. Sorry, negative 1.1 over 1.407. So this is 1 plus negative 1 over 1.407. And finally, we can figure out what that is. Go to a calculator real quick. 1 minus 1 over 1.407 is 0.289. So this area here, the area beneath the income curve is 0.289. That's this area down here. What we really want to compute is this area between the two curves. So we're going to have to do 1/2 minus 0.289. which is 0.211. And then we can double that to get a Gini index of 0.422. The Gini index is a real thing. Oh, sorry, it's Corrado Gini, not Lorenzo Gini. It's the Lorenz curve. And it is a simple measure of distribution of income. So, for example, let's see if we can grab some data here, maybe from the World Bank. So the Gini index for the entire world is currently somewhere around 0.65. Let's see here. And the Gini index of the United States is right around 0.414. So this island nation has income inequality roughly equivalent to the United States. Okay. So the quiz I'm handing out basically has you do this, but instead of using a fictional group of people that distribute wealth based on seashells, instead they are. I'm going to have you use data from Colorado. So you guys will end up computing the Gini index for Colorado itself. So hopefully that should be vaguely entertaining and somewhat useful and interesting. Does anybody have any questions about the Gini index so far? I think this is going to make more sense once you guys have tried to do it and worked through the problems a little bit. But if you have any questions right now, I'm happy to try and answer them.
Can you scroll up a wee bit?
Sure. Like here?
Yeah, that's good. I just need to get the whole equation that's in the box.
Yeah. That equation is on the quiz. So. Okay. So that leaves us with kind of a short one for today. I don't have a lot of other stuff that I really want to get to today. I don't want to start getting into substitution method yet. That'll be the next thing we talk about. So I think I will probably just cut it off here and leave you guys with the quiz, unless anybody has any other questions. So basically, I want to give you guys the rest of class time to either work on the quiz and ask me any questions you have about that, or work on your optimization project and ask me any questions that you guys have about that.
Do we turn in this quiz?
Yeah, I'll put a box in D2L, and you can turn it in the same way that you did your exam. So either annotate a PDF or take pictures of it and send the pictures. If you can print it out and write on the thing itself, that would probably be ideal. But if you need to do it on a separate sheet of paper, that's also fine.
When is this due?
Oh yeah, this will be due on Monday, so next class. Actually, you know what? Let's give you guys a week to do it. I'll have it due on Wednesday of next week, alongside the next part of the project. So the quiz will be due on the 22nd. Okay. I will stop the recording here.